Thank you very much for coming to hear this about engineering in hospitals and how engineering systems can help us reduce infections. So, as I say, I'm a member of these societies, and there's a bit more about me in one of the slides. And I put this in partly because I want to draw your attention to two things. First of all, back in 1981, I was a member of the Low Energy Hospital Study Group, and the Department of Health wanted us to find out if we could reduce hospital energy consumption by 50%, which we did, and they built two hospitals, the Isle of Wight, St Mary's, and Wansbeck in Northumberland. So as far as I know, they're the only two that got done, but it shows we can save a lot of energy if we want to. And I mention that because in reducing infections, we do have some opportunities as well to reduce energy and to reduce carbon. And reducing carbon is something that you will be involved with in the next few years. Further down here is the member of the research design study into low energy ventilation and cooling of hospitals, which was run by the Department of Health back in 2008. That study has never been published, but the intent was to use more natural ventilation for cooling, and I do mention that in this presentation. So I was aware very much of the need for proper infection control when I went into this hospital. It happens to be 5 miles from where I live, and it was for bone surgery, of course. It's deep surgery, and this is where John Charnley, who was a mechanical engineer like I am, he became a surgeon and started doing hip operations. And he worked with somebody called Howarth in Bolton to develop the Charnley-Howarth clean air system. He realised at that time that although you might do some wonderful operations, if they weren't in a clean environment, then he basically failed. And you can see the kind of lengths they went to in those days to stay clean. Now, we have better systems these days, of course, but the importance of staying clean is as much as ever. So the overview is that we're looking at airborne infections predominantly through ventilation. It's still a problem. People think COVID's gone away. It hasn't, of course, but it's more than COVID. There's a lot more in the air that we need to take out if we want to have clean environments. We can reduce this by effective ventilation. So I've used the word effective there because it's got to be done properly, really. And better and cleaner ventilation can actually reduce energy costs and reduce carbon, and we must take that opportunity. There is this desire to get to net zero, which I'm going to mention. We have options and strategies to think about, and there's various targets to bear in mind. So I think the first thing I should say is engineers and me, like me, are about applications. We're about doing things that actually work well. That's what we want to do. So we're not doing research for the sake of it, not producing numbers. It's the outcome that really matters. And in that, we have a set of codes of practice. So a code is like a legal requirement, if you like. It's a deadline that we have to meet or something we have to overcome. And so we tend to want to use proven technologies. We don't want to take risks. But on the other hand, we do need to be innovative. So if we're going to be innovative, let's try and make sure the innovation works. And so as we go forward, we've got to be aware there are drivers here. There's the carbon challenge, there's cost, of course, reliability, and how we can create this well-being environment for people. And I just sum this up here. The legislation is coming from government and others. Climate change agenda is getting more and more serious. I was told on a meeting I went to the other day, if we don't, as a world, start reducing carbon within 9 years, we might as well give up, because apparently we're not reducing, we're going up day by day. So we've got a very short time to actually get started meaningfully. The National Health has net zero targets. Your target in the National Health is to be completely net zero by 2040, and for every new hospital built or new part of a hospital to be net zero straight away. And then we have this overriding commitment to improve the experience for our patient. So I just wanted to show this slide because the old thinking used to be we could become net zero by reducing energy, making systems efficient, and then putting renewable energy on. But in fact, the latest thinking is there's 5 steps, starting with behavioural change, and that's really where a lot of us come into this. We can do quite a lot, and I'm going to point that out here, by just changing the way we do things, and then we have to think about the other things like better engineering systems, using thermal energy better, not wasting it, and some renewable energy. That will be inevitable. And I've listed here, and I won't go through this slide because I've I've got to be on time for this second speaker, some of the ways that we might hit those 5 different categories. You can see those later. So the shocking thing which I discovered during COVID is that 56% of our hospitals don't actually meet our code requirement, which is HTMO3, of course. So they're below the minimum standard. Don't think of a code as something you try and hit. It's something you ought to be way above. You know, and if you really drop down, the code is something you mustn't fall below. It's like a speed limit on a road. If the speed limit's 30, you shouldn't be doing 60. The speed limit's 30. So some of the hospitals I visited had no ventilation at all, which I thought was shocking. An airborne infection is inevitably rife. I think we all know that. So HTMO3 is the minimum target, and we've got to make sure we go above that. Poor ventilation will impact upon performance in many ways, and from your point of view, you will have patients staying in hospital longer, visitors to the hospital and staff becoming ill because the environment there, the atmosphere is not fit and healthy. So better than code must be our intention that we want to keep. So we will also find that if we get this right, we will save ourselves a lot of money. So we want to exceed the minimum air change an hour in the code. We want to mix recirculated air, which is cleaned air, with incoming fresh air or outdoor air. We need to do that. We don't do that at all in any UK hospitals at the moment, apart from the hospital I worked on in Newcastle, which I'll show you in a minute. But the people, generally speaking, it's not allowed. Well, a new version of HTMO3, which came out in 2021, towards the end of the year, does allow recirculation if you clean the air using UVC or HEPA filtration. The way we supply the air is important. And their strategy generally should be from the clean areas towards dirty areas in a cascade environment. And we have to be aware of this word, effective. So this is HTMO3, which I think you're all aware of. You can download it from the NHS website, of course, and it gives you a table of air change rates. But before I go to that, I thought I'd show the American standard, 170. So I'm on this committee as well, and the way that they do it is slightly different. The air change rates are pretty similar numerically, but if you look, their amount of outdoor air coming in is only 2 air changes an hour, and the amount of air they recirculate could be 8, 6, 10, whatever, but it is cleaned air. It's not just the same air going around. It has to be cleaned. So that's a very different approach, and that's pretty standard in North America and other places like that. A lot of Europe is full fresh air as well, by the way, so we're not on our own, but I think it's something we have to embrace if we really want to get our carbon figures down, and if we also want to meet our standards. So this is HTMO3 here, and this is the page which gives us the air change rates, and you see the numbers. It doesn't really mention recirculation, it just gives you 6 air changes for wards, 10 air changes for treatment rooms, 15 for bronchoscopy. So these are the amount of air changes that we'd want to bring in. So a treatment room at 10 air changes is meaning every 6 minutes we remove all the air from the room, throw it all away, and bring a new lot in, which is quite a big energy penalty. And as I say, because more than half our hospitals don't actually do that, if we start doing that, it's going to cost us a lot of money in energy, a lot more than we're spending at the moment. So we need to find a better way of doing it. And the way to do it is to recirculate that air and to clean it so that we come up to the air change rate we want with whatever the air change is now, plus recirculated cleaned air. So if we want, we've got 5 air changes coming in, and we need 10, then we'd have a recirculation system cleaning the air to give us 5 to add to the 5 we've got. So definitions here, ventilation air, we tend to call it fresh air from outside. Outdoor air isn't necessarily fresh. It can be quite dirty and mucky, and we need to always filter it, clean it, and heat it, of course. In summer, we'll cool it. The air change rate would be the actual air supplied to the room, which could be a mixture of the outdoor air coming in plus any recirculated air we've got. And ASHRAE standard 170, that really defines it in that way. The Americans have actually really only got into this in the last 15 to 20 years, and they produced this design guidance, and there's quite a lot of good information coming through from that source now. There's a number of controversial issues, and I won't dwell on them too long here, but we have a choice of whether we have air change rates, so we could just stick to say 10 air changes, or we could go for less air changes and recirculate with UVC air cleaners or with HEPA filtration. There are other methods of cleaning the air as well, by the way, which we might want to consider. The temperature is important. Humidity is something we don't really worry about too much in the UK, but there's strong evidence that keeping the humidity level between 40 and 60% relative humidity is the best to reduce infections. And we might want to consider that going forward, but at the moment we tend to ignore that fact. Here's a graph showing the relationship between the risk of infection. So if you haven't got any air change coming in, you've got a pretty strong risk of spreading infections in the room. However, if you get to 6 air changes on there, that risk is reduced to 25%, and that's the figure we use in wards, which is a higher figure in other places. Now, when we think about ventilation in hospital, we need to realise that all of these spaces, and this is a central street in the Erasmus Hospital in Rotterdam, as an engineer, I'm looking at a ventilation shaft that's carried air through it, which could be part of my ventilation system. It could be that I'm exhausting air into that space, or it could be that I'm drawing air from that space into the hospital, but it has air in it that is part of the hospital ventilation system, and we need to consider it in that way. Which air is moving to that, which air is moving back. In terms of behavioural change, I have a case study here of a hospital in Newcastle, which is the Freeman Hospital. I was brought in as a specialist engineer to do a ventilation upgrade because the contractor had built this department with all the radiotherapy treatment rooms receiving 5 air changes an hour off of a mechanical plant on the roof. So I've refurbished this one room at a time. It's all complete now. This has been approved by Public Health England. It's fully operational, and I would suggest these are probably the cleanest rooms you're going to find in any UK hospital. And the way we did that was to put in packaged air handling plant in the room itself to give me 10 air changes an hour in that room, and that air goes through filters, HEPA filters, which cleans it down to the level we want. But we still keep the 5 air changes which came from the plant on the roof. So we now have 15 air changes an hour. And incidentally, I want to draw your attention to the fact that in HCMO3, we don't really have any HEPA filters in the hospital apart from very specialist areas. We have an F7 filter. That's usually the best grade we work on. So we've introduced the HEPA filter here in the recirculation air to be doubly sure that it's clean air. And the reason I couldn't do this with a ducted system and a big fan on the roof is because each of these radiotherapy rooms is a bunker where the wall is 1 metre thick concrete. It's got extensive steel in it and completely lead lined. And any hole, even a hole for a pipe or a piece of cable going through, has to be protected so that the gamma rays and other radiation can't get out of the room into the surrounding areas, which is where the carers are. So we didn't have much option other than to do it in the room, which is what we did. And this is some pictures of these rooms. There's a number of different ones. It was a major upgrade with all the ceilings coming out and replacing pipework and everything. And this installed package had to be accessible from the room itself. It's not in the ceiling void. It's actually in a drop-down bulkhead, which can be easily accessed and serviced inside the actual treatment room. This is another one of the rooms. In this particular room, I put the unit into a cupboard in the corner as a vertical, if you like, a wardrobe type unit, and open the doors, and there's the air cleaner unit in there, taking the air from low level back up into the ceiling and circulating in the room. So this was a major way to improve the air handling without spending an awful lot of money on new air handling plant and ductwork, which would have been impossible anyway. And to do it without really using any more energy because we're recycling the air in the room. But what I did find from that project, and this is probably pretty common across the health service, is that we are operating this plant 24 hours a day, 7 days a week, although the rooms themselves are only used for 12 hours a day. And I couldn't get the Estates Department to change that. They like to keep it like that. So when the room's empty at night and there's no one in it, there's no infection risk. We don't need to run the plant. We can switch it on in the morning at the time we need it, and everything will be fine. But they don't want to, if you like, take the risk of it not starting. So that's what we do. If we were to switch this kind of plant off, we would instantly save 50% of our energy in that particular part of the hospital. So again, another major opportunity to reduce carbon if we want to hit these carbon targets. Moving forward into the effect of COVID that we had, I wanted to bring your attention to some of the work we did there. The Royal Academy has produced this report, which you can download, and that really highlights the issues around COVID, which are more economical than anything else. And I wanted to tell you that we've been working on 2 new standards for air cleaners for the NHS, which are going to be published, I think, around the 9th of May. So the first standard is for UVC, which is ultraviolet air cleaners, and the other one is for HEPA filters. And these are the kind of devices you're seeing in the exhibition there that you might want to buy, just to make sure that they come up to standard, they're going to do the job you want, they're reliable. So these highlight the engineering requirements. They don't list any names or direct you to use anyone in particular, but they're really directing you away from the ones that perhaps don't work too well. So we've got those done. And I also wanted to share with you a story of St George's. This is a hospital I worked on around 45 years ago in London when it was being built. I was part of the contracting team. And my brother's in the hospital. He's in bed here and you can't see him, but he's part of my family. So we were visiting him because he was very sick. And I was shocked to find this ventilation, it's completely inadequate for modern day, but there's been no attempt to upgrade it. So this is the ward he's in. The ventilation is opening a window, although he's got a serious case of cancer. And there's been no upgrade at all. But worse still, the nurse stations are out in the corridor. And I couldn't really understand this. So the nurses who are observing him and other patients in the wards on either side sit in this corridor at these workstations. And guess what? There's no ventilation in that corridor. I just can't explain that as an engineer, but this is what's going on. So I think we have a major task on our hands to do something about this. We need to upgrade our hospitals to meet the minimum standard, be better than the minimum standard. And when we're doing it, we want to take the option of saving carbon at the same time. So one solution we're looking at might be introducing the role of an infection control engineer. Someone like me, go down, have a look, write a report on what's happening, what's inadequate, and what the solutions are. We want to look at mitigation. Do we use more air to dilute it? Do we use cleaner air to remove the contaminants? What are the airborne risks? This is what we need to highlight. And then if we're going to look at air cleaners, whether they stand in the room or they go in the ceiling, how are we going to use those? So we've used a lot of these so-called portable units. You remove them from the box, and I think what I would say with those is they're great as a temporary measure, but I don't see them as a long-term measure. So I'm working with people and the NHS as well to get units to go in the ceiling, out the way. They're part of the infrastructure. They'll recirculate and clean the air, and they're not in your way. They're not using a socket up. They haven't got a lead in front of you. They're just simply popped up into the ceiling void. And the other way of doing it is to get them into the ductwork system that's serving the room already so that we can clean the air and recirculate the air in a hospital that way. So this is really going beyond it. Beyond COVID now, we've really got to think seriously about the ventilation standard in the hospital and how we can make that better. And this really highlights those 3 options: the mobile standalone units, the in-ceiling units, or units in the ductwork. I think with the okay, I've got 1 minute. Okay. I think the mobile units you can remove from a box and plug in yourself. Great. If you're going to use the ceiling units or the in-duct, you're going to have to call someone like me in to say, where does it go and how do I connect it up and make it work properly? So that's a bit of an engineering job. But at the end of the day, it's the more proper infrastructure type role. There is chapters of information about things like UV and filters to get, and I think the other things you can find is quite a lot of information available on websites, which I'm giving you in these links, so you can follow those up. This is a typical bit of kit. This one's outside, actually, although I think he's gone now. And this has really been developed in conjunction with the NHS, where Professor Fisher met these people and indicated, the kind of thing that he wanted to see, and they've been developing them. So there's a couple of British-based manufacturers that have come up with products, but there are also imported products which you can consider. This is my mother-in-law in a care home, and she's been experiencing the use of one of these. She is still there. She's 96. This particular care home lost 10 people, but she's still there. So I think some of this technology is good.